Air pollutants are just something in the air that's considered harmful. And we determine air pollution levels using a couple of factors. The amount of pollutant that's going into the air, the amount of space into which it's dispersed. So let's say you have a pollutant going into a very large space. It's not going to, that your air pollution level is not going to be too bad because, you know, it's going into this really wide space. It can disperse really well. But if you're having that same amount of pollutant going into a really small space or a space where the air doesn't circulate very well, then that's going to be much worse. And then we also talk about how we remove the pollutants from the air. So if there's a way to remove the pollutant, then it's not going to be as bad as if there's no way to get rid of it. So one of the things that we have is something called industrial smog, and it basically is dust and smoke, and it comes together and it makes this smog. And it's basically soot, sulfur compounds, and water vapor. Most of the time it's in the winter, and we really don't have a lot of it in the United States right now. But you'll see it a lot in China, India, Korea, and Eastern Europe. There was a point like in England where it was in the 50s, and the air quality was so bad that like they literally couldn't see. It was like this haze like this over all of, and people wore these like they have these things, and they would wear these like bubble thing kind of like this, like around their head, like I know it sounds like a joke, but they would wear stuff like that around their head, and got better obviously because they don't wear that in England anymore, but that was a really, really bad thing back then. And then we have a special type of smog called photochemical smog, which we do have a lot in the United States, especially in urban areas. So if you live near Atlanta or in Atlanta, this is where this is from. And if you live in counties around Atlanta, your cars, I don't know if your parents have ever talked about it or you've seen the signs on the side of the road, they say like emissions testing. Basically, there's because there's so many vehicles and it's such a big problem around Atlanta, they actually, in Atlanta actually have to meet certain emissions rules. And every year when you go to register your car, like I have a car that's due for registration in April, we have to take it to an emissions testing place and they'll test the emissions, and then we have it's they give us a paper, but it's also electronic. So when we go to the office to file for to update our tags, it shows that that car had emissions testing and it passed or failed. Um, and you have to have that in order to register your car. So basically, photochemical smog is when we have nitrogen oxides and VOCs, basically vehicle exhaust, get acted upon by sunlight. So sunlight hits them, it causes a chemical reaction, and it creates this photochemical smog. It basically starts when folks start commuting in the mornings, and then it doesn't go away until like the evening commute or after the evening commute, and it's just this like haze that kind of sits over the area. Then we have what we like to call temperature inversions, and this is when we're going to have cool air below warmer air. This should say below, not betlow. This usually tends to occur at night when you've got that cool air, that lower cool air. But what it does is it kind of traps the smog down by where the people are in the lower part of the atmosphere. It makes the smog much worse. And the smog can cause headaches, nausea, eye throat irritation, asthma, emphysema. It can irritate those. I remember when I was in middle school, my family went to LA, and I wore contacts, and I also had childhood asthma as a kid. Obviously, I had childhood asthma as a kid. It was when I was a kid. But my eyes turned like really, really red when we were there, and I like my contacts hurt, and it was really painful, and it was because of that smog and stuff that's there. Now we have this other thing called the atmospheric brown cloud. Again, we don't see this a ton in the United States, but we do see it in some places, but it's big in Asia. It hovers over South and Central Asia, and it's just thick layer of pollution. It's you're gonna have a lot of black carbon or soot, And this is because they burn biomass and they burn fossil fuels a lot, and they burn not clean fuels, and so they tend to get this little haze like you see in this picture right here. So then on the AP exam, a lot of times they will want to know, they'll ask you about the primary pollutants, or they'll say list a primary pollutant or whatever. So your primary pollutants are particulates, and those come from industrial combustion. VOCs, which is also from combustion of fossil fuels. Carbon monoxide, which is the combustion from cars. That's the thing where like you don't want to have your car on in an enclosed space like in the garage. If you've got your car on, you don't want to like close the garage door because the carbon monoxide will build up, and it's silent and it doesn't smell. It's clear. It can kill you. NOx is combustion. This causes from burning fossil fuels for cars, but also burning wood. SO2 is burning from power plants mostly. And then lead, and this is from basically the burning of lead or making batteries. And then they have this vague one called air toxics, which is from cars. These primary pollutants will mix with other things in the atmosphere to form secondary pollutants. And you need to know the difference between the two on the AP exam, because sometimes they'll ask, like, which one is a primary, which one is a secondary. Or there'll be an FRQ that says, name a secondary, name a primary. So ozone is a secondary pollutant, and it forms when VOCs react with NOx. There are peroxyacetyl nitrates, which is when VOCs also react with NOx. Sulfuric acid, so that's when that SO2 reacts usually with water vapor, and it takes the hydrogen from the water vapor and produces sulfuric acid. Same thing with the nitric acid, it takes that NOx and it takes the H from water vapor and forms citric acid. And then the sulfuric acid and the nitric acids, both of those form acid rain. Okay, and the reason they're called secondary pollutants is because they are not directly released from any activity, but they are formed from other activities. One student mentioned that lead was a primary and a secondary pollutant, which is not really possible. Lead is a primary pollutant because it's, lead is what is released, and a secondary pollutant is formed from primary pollutants. And so lead can't, lead is lead, right? Just like nitrogen is nitrogen, oxygen is oxygen. So lead is not going to be formed from anything that is previously emitted. Now, it could be some compound that has lead in it, could be a secondary pollutant, but lead in is of itself would be a primary pollutant, not a secondary, because it's not going to be mixing with a primary pollutant to produce lead. So if we talk about these secondary pollutants and how they react, or how we react to them, ozone is a result of chemical reaction. This should say reactions between NOx and organic compounds. And an important thing about ozone, which students always mix up, and it's not you all in particular, just in my time of teaching this course, I've seen this happen a lot. So if this is the Earth, right? We'll do this. If this is the troposphere and this is the stratosphere, okay? Ozone down here is bad, right? We don't want ozone down here. It's considered a pollutant. It's bad. We don't like it, okay? Ozone in the stratosphere is the ozone layer, which basically protects us from radiation from outer space. So it's good. Okay, so a lot of times students get confused because we say ozone is this terrible pollutant, but then we have this ozone layer that we like. So ozone that is close to the surface of the Earth is bad, and ozone that is in the stratosphere or much higher is good because it protects us from radiation from space. So that's kind of the difference between the two. Acid rain is basically any rain or any sort of precipitation. So you could have like acid snow, or you could have acid fog. Anything that's more acidic than usual. Thinking of acid fog reminds me of that part in the Hunger Games where they're like in that maze or whatever, and that not the maze, the clock, and they're Katniss and like Finnick, and they're running away from that mist. That's sorry. That's what that reminds me of, that like fog. Anyway. And then acid deposition is when we have acid rain, but also some dry particle fallout as well. And so they like to, a lot of times people say acid precipitation, but acid rain is kind of like the common way to say it. And then this is just kind of like a review for folks that maybe haven't had chemistry or don't remember chemistry very well. So acids release hydrogen when they dissolve in water. So you can have, the most common ones are hydrochloric, sulfuric, nitric, phosphorus, acetic, and carbonic acids. And then bases release hydroxide. Okay, so hydrogen ions would be like an H plus, and hydroxide is like OH minus. Okay, so it has a plus, it's an acid, and if it has a negative, it's a base. Basically, if it releases one of those. Okay, and then these are some common bases. So here's our pH scale. This is neutral. Water is really expected, like really pure water is expected to be neutral. Anything with a pH higher than 7 is a base, and anything with a pH lower than 7 is an acid. And this is like a logarithmic scale. So for example, something that has a pH 1 is not like 1 times more acidic, it's 10 times more acidic. Okay, so like you see these, you have like a 1 or a 0 is a battery, and then a 2 is a lemon. So it's like, whoa, but it's actually 20 times, this is 10 times, and this is another 10 times. So the lemon's like 20 times more acidic than the battery, even though it seems like it, they're really close on the scale or whatever. So that's kind of just like a little review of acids and bases in case you need it. So acid rain usually has a rainfall in general anyway has a pH of 5.6. So rain is already like a little bit acidic to begin with. But then acid rain has a pH below 4.6, right? So it doesn't seem like that much, but it's 10 times, right, more acidic than the 5.6. And in the eastern United States, because this is where we have a lot of industry in the eastern United States, we have a lot of areas that are really highly populated, right, as compared to the West Coast. And so, excuse me, that's why we've got more acid rain in this area than we have like in other areas. And you'll find this in the United States, Europe, Russia, China, Japan, basically places with a lot of industry, or places where you have a lot of people living really close together in industrial areas. Acid rain can cause some crop damage, and so can ozone. That's what this is supposed to show you, ozone. The leaves will have like black flecking, the leaves can yellow, the plants can just die, or the leaves can fall off. And this losses due to air pollution in general tend to be about $15 billion a year. And these are statistics are a couple of years old, so they might be even higher now. But that's a lot of money, right, from air pollution. Then exposed surfaces can turn gray and dingy from acid rain. Paints and fabrics will deteriorate more quickly due to air pollution. Rubber, anything that's rubber will crack, metal will corrode. You can see like this stonework is really deteriorating from pollution. It also can affect visibility, like how well you can see or how far you can see. Excuse me, I'm really yawning. Some things that can happen with acid rain in aquatic ecosystems. So most aquatic ecosystems, their pH is between 6 and 8. Really, they tend to be pretty neutral. And so what happens when you have a lot of acid rain is it reduces the pH of these places, and the animals that live in these areas um, aren't adapted to these pHs, and so they die, or they're not going to thrive anyway. These are, you can see these trees, they have been exposed to acid rain. They're more likely to freeze in the winter because they don't have those leaves. The pine trees will lose all their needles. And then sugar maples actually are very susceptible to acid rain, and they can between 20 and 80%, which I know that's like a huge, excuse me, broad statistic, like 20 to 80%, like 20% damage. So, well, that's not that bad. 80%, well, that's really bad. So it's a big difference. This is, I think, a picture of it's either Philadelphia in the 60s or England during that 50s smog. I want to say Philadelphia, but could be England. But you could see, like, this is what it used to look like, and I don't know anywhere that looks like that right now, right? And so the Clean Air Act is working, right? It was passed in 1970, and then they amended it in 77 and 90. And the Clean Air Act is one of those acts that there's a few acts throughout the course, like the Endangered Species Act, the Clean Air Act, Clean Water Act, that I would kind of like know the basics of, and I would just kind of like basically like kind of keep them in your back pocket. And so, because sometimes for an FRQ, they will ask you, name a piece of legislation that affects this issue or something like that. And so if you pick some really broad acts and you kind of get to know them, and you just remember a few, then you could do something like that. Like, for example, if you remember the Clean Water Act, and they're talking about an oil spill, right? You could say, well, the Clean Water Act says, blah, blah, blah about clean water. And that's a lot easier to remember than like the Oil Pollution Act of 1990 or something like that, right? So if you remember like a few broad pieces of legislation, and just kind of have them ready for the AP exam, it's a little easier than trying to remember every single little intricate law. Like the Endangered Species Act, right? You could use that even for an oil spill, right? Because it might harm if it happened in a place where an endangered species could have lived, and so that kind of thing. Anyway, I digress. So the Clean Air Act basically identifies widespread pollutants. It sets standards for what like the ambient amounts can be for these pollutants, and it establishes methods to control these air pollutants and timetables, like, oh, we need to have them done by this time, or we need to have it like this and by this time, or something like that. So that's kind of what the Clean Air Act does. Then we have these national ambient air quality standards. They have something called criteria pollutants, and that's all the primary pollutants in lead. That's why a lot of times people consider lead a primary pollutant, because it's really specific, but because it's listed with there. And then the primary standard for each pollutant is based on the presumed highest level that could be tolerated by humans without an ill effect. So you can see, for example, like carbon monoxide over 8 hours is like 9 parts per million, but then lead is like 0.015 or 0.15 micrograms per meters cube, right? So that's like very, very tiny amount. And so it just depends. It's different for each pollutant. It's not like there's one primary standard that is the same for every pollutant. And so then there are ways that we can limit vehicle pollutants. Basically, cars are almost half of our pollutants that are released into the atmosphere. And so they mandated a 90% reduction in pollutants. That was really unrealistic, but by 2007, cars emitted 86% less. So that was a lot better. But you could see if you had a really old car, right, and then you had to get emissions testing for your car because you live near Atlanta, your car might not pass emissions testing, and they might have to do something to your car to get it to pass. One of the things they do in a car is they've added these things called catalytic converters. And these basically convert NOx to nitrogen gas, and it turns carbon monoxide into CO2, which nitrogen gas is not such a big deal, but CO2, you know, it's like is also a pollutant, but I guess they decided it's not as bad as carbon monoxide. And this has been really significant in controlling pollutants. So the Clean Air Act has been changed to require cars to emit 30% less VOCs and 60% less NOx. And then interestingly, buses and trucks have to meet even more stringent standards. You would think that they would have to meet less because, you know, they're so big or whatever, but because they're traveling all the time, I guess, they decided that those folks should actually meet more stringent standards instead of less. They've started adding oxygen to gasoline, which also cuts down on carbon monoxide emissions. And then these emission measuring stations, right? That's what I was talking about, where you have to get your emissions tested. They have to measure your emissions pretty accurately in order for you to know. Then they have something called CAFE standards, which is part of the Energy Policy Conservation Act. See, it's much easier to remember the Clean Air Act for your AP exam as one of those laws to have in your back pocket than the Energy Policy and Conservation Act of 1975. That's a lot longer. So these places, this act actually sets corporate average fuel economy standards, and we've never actually met the standards, but it has really increased the fuel economy of vehicles. So people like that, right? Because the more economical your fuel cost or your fuel usage is, the less you have to spend on gas, and also, you know, the less pollution you're going to be emitting. So, and it also increases the range of your tank, right? And then we have an Energy Independence and Security Act, and it basically mandated that the CAFE standards went even higher. So here you can see kind of what the CAFE standards look like for different vehicles. And so why did they want to raise these standards? So there's a few reasons. One, the more efficient your car, right, the less gas you need. So it's going to reduce our dependence on foreign oil. The less that you're emitting from your vehicle because you're using less gas, the less smog and particulates will be emitted, and the less carbon dioxide will be emitted. So I'm sure there's a negative, like, oh, it's going to cost money to figure out how to make these cars more fuel economical or whatever, but basically the CAFE standards are pretty decently good all around. Excuse me. Another thing that has really helped is hybrid electric vehicles. These vehicles are gas and battery powered. They're very, very fuel efficient. They can get over 40 miles per gallon. The Prius is the most efficient car in the US when this was written. Now we have like the Nissan Leaf and the Tesla and all that kind of stuff. My sister has a Prius, and my dad is like the most, I mean, he drives an Excursion, right? It's like, can you get a bigger vehicle? And he actually thinks her Prius is pretty cool. So that's kind of neat that he's kind of coming over to the light side, I guess you might call it. And these cars are more expensive than traditional cars, but a lot of times you get a tax credit or an incentive. One of the things to remember with these is the batteries are very, very expensive, and they usually have a lifespan. And so it's not like a normal car's battery. It's like a special battery. And so a lot of folks, like my husband, he commutes pretty far, so he was looking at a Prius, but we can't afford a new one. And a used Prius, you know, how much life are you going to have in that before you have to buy a new battery. So it's like kind of an economic decision for us. So that's kind of something to also think about, as that people have to think about as well when they're doing stuff like this. So now let's talk about ozone a little more. So we can talk about point sources and non-point sources or area sources. So point source is a place that you can definitely say, okay, the pollution is coming from that factory over there. That would be a point source because you can point to the place where that pollution is occurring. Okay. A non-point source is a place where you can't pollute, you can't point to where it's like agricultural runoff. You can't tell which farm is producing the runoff. You can't, you know, it's not very specific. If you've got a whole bunch of farms and it's running up into the water, you can't tell, oh, it's coming from that versus that, right? So that would be like a non-point source. And so industries are about 30% of our emissions from ozone. Then we have some non-point sources, which are about 20%, and then the rest of the ozone is like 50%, right, is from cars. And so then they came up with these tier 2 standards, which means that SUVs, trucks, and vans are now held to the same emission standards as cars, where they didn't used to be. They used to have different standards, but now they're the same. And so then they came up with the Clean Air Interstate Rule and the Clean Air Mercury Rule. It basically, we wanted to reduce mercury emission and set lower caps on sulfur dioxide and nitrogen oxide. A lot of people think that these aren't very strict, but it's what we've got, right? Until the EPA fixes it. Well, right now, I don't expect that to happen anytime soon because, you know, our current administration isn't really a huge fan of the EPA. Let me see if I can close the door. I can hear my kid in the background. Okay. He and my husband were playing. I'm not really sure what they were playing. So we've reduced SO2 emissions by about 50%, which has really reduced acid rain or acid deposition. And then basically what they do is companies get what they call emission allowances. And so you don't get new allowances, but basically like they made a certain amount of allowances and they distribute them between the companies. And then they said, okay, these are the allowances that are there. That is what it is. And so like if you don't use all of your allowances, you can sell yours to someone else. Or you know, if you need more, you can buy some from other people. And that's really reduced nitrogen oxide emissions. Okay, now in order to talk about a couple types of ozone, we need to talk a little bit about the electromagnetic spectrum. This is kind of a physics thing, so if you haven't had physics, I'm gonna kind of give you a quick and dirty rundown of the electromagnetic spectrum. So radiation is basically part of the electromagnetic spectrum. Let me see if I can circle it for you. This is like one of my least favorite lessons. It seems really boring to me. So here's your radiation, right? You have like ultraviolet radiation right there. But so is like, you see visible light is here, infrared. So we've got, you know, a few kind of important things. And so UV radiation can damage protein, it can damage your DNA, but most of it is absorbed by the ozone layer, right? And so we have, this is our planet. Let's say that's not to scale. And then this is the sun, right? This ozone, this UV radiation hits the ozone layer, and then the ozone layer absorbs basically most of that radiation. It lets the light through, but it keeps the radiation out, the light and the heat. Okay, so that's going to really protect us. If we don't have that ozone hole, right? If we don't have this ozone layer, then that stuff can get straight through. Okay, so that's kind of where the issue with the ozone hole is why we're worried about it, why we care. Okay, now I have actually seen an FRQ where they ask you for these equations. I'm not even kidding. They say, how is ozone formed? How is it broken down? And they say the student can provide the equations, or the student can write in words or in sentences what is in the equations. So I would recommend that you know these. I myself, like if I was in AP Environmental Science, I know myself, and I know that that is something that it is highly unlikely my brain is going to memorize. I still have to look it up. I don't have these equations memorized. And so for myself, I don't know that I would spend a ton of time memorizing that. I would kind of like, um, roll the dice, I guess, and not memorize them. I would know what's going on here, but the actual equations, personally, I probably wouldn't memorize. Just like I know that I am not very good at memorizing dates. It is going to take me twice as long to memorize a date as it will take to memorize like 5, 10 different facts, right? So I just don't bother memorizing dates. If they ask me what year was the Clean Air Act done, honestly, I know I just read it. I don't know, right? I can't remember numbers like that. It's just something, well, with my brain, it doesn't work. So I would just spend my time memorizing more facts and learning more facts than I would trying to memorize what year the Clean Air Act was enacted. And then if that question came on the AP exam, I would know that, well, that's one I'm going to miss. But that's me personally, right? You kind of have to do your own cost benefit analysis. What is it worth it to you? What is it worth to you? But that's just me personally with these equations. But I would know what's going on here. So what do we have here? We've got oxygen reacting with sunlight, and it's just producing two like oxygen radicals, right? And then this oxygen radical will react with another O2 in the atmosphere and produce an O3. So every one of these reactions will give you two ozones. Okay, do you see that? And then you'll have an oxygen radical can mix with an ozone and give you two oxygens. And then the ozone can react with UV radiation to form an oxygen radical and O2. And then that oxygen radical can either form with an O2 to get an ozone, or it can form with an ozone to get an O2. So the amount of ozone in the atmosphere, which are the O3s, right? O3 is ozone, which is not good, and O2 is regular oxygen, which is like that's what we breathe, which is good. And so it's constantly changing because these reactions just kind of like back and forth, back and forth, back and forth. So that's kind of the part that personally I would memorize, but technically I have seen on the AP exam where they ask you about these formulas. So what are some things that are the worst at protecting the ozone layer, or that hurt the ozone layer the best? I'm, I'm not saying it right. But basically, chlorofluorocarbons, which they call them CFCs. For the AP exam, if you say CFC, they know what you mean. You don't have to spell out chlorofluorocarbon. You can just say CFC. These things are non-reactive, they're non-flammable, and they're non-toxic. And they have some sort of like halogen in them. Okay. So this CFC will combine with UV light, produce a free radical of chlorine, and then this thing, that free radical of chlorine will react with ozone, and it breaks up that ozone. See, it's taking the ozone away. And then this, the ClO and ClO will combine to form two chlorine and two oxygens, right? So this is what's causing the ozone layer for us to lose the ozone layer. And the big problem is, you see how we have the ClO doing this, right? We're constantly making more individual chlorine, which is then breaking up more oxygen, making more individual chlorine, breaking up the oxygen, that kind of thing. So they call it a catalytic cycle because it's constantly happening. and the chlorine is basically a catalyst for breaking up ozone. So that's why these things are a problem. And these were found in like refrigerators and things like that. Aerosol cans. This is a more detailed picture of what is happening here with these with the ozone layer. So what's up with this ozone hole, right? It was noticed in 1985, and they thought it was about the size of the United States. Okay, that's what it was in 1984 and 1985. They actually noticed it. In that area, ozone levels were 50% lower than normal. So it wasn't exactly a hole where there's like none left, but you know, it's a lot less than normal. And then this is Antarctica right here. So it's actually basically what happens, and you can see this in this picture, is the chlorine actually kind of starts hanging out right here. And since the chlorine is hanging out right here, that's where the ozone hole formed. Okay. And then you can see that summer chlorine or summer conditions can cause like more chlorine to be formed and trapped, which sometimes can prevent ozone depletion. But anyway, you know, I thought the hole was getting smaller, but it doesn't really look like it is in these pictures. So then everybody, when they realized that the ozone hole was happening, they quickly came together and created this group called the Montreal Protocol. A bunch of countries came together for a meeting. They said, what are we going to do about this? And they decided they were going to scale back CFC production by 50% by 2000. But then they realized that CFCs were causing the ozone hole, and it was much worse than they thought. Like they were causing it in a much worse rate than they thought. They moved the target date back to 1999.